In this video, we're going to define the important concept of an invertible linear transformation. So basically the inverse of a transformation. And the analogy is what I could say is going back to when you started studying functions, let's say in algebra, and you learned under certain circumstances, some functions have inverse functions. And then you learn of a procedure of how to find them. Well, that's what we're going to do for linear transformations. We're going to be able to identify when a linear transformation is invertible, and then it turns out we already know how to find that inverse. And believe it or not, and if you think about it, it's going to be related to the inverse of a matrix, right? So let's start with a couple key definitions, right? So let T from Rn to Rm be a linear transformation. All right. First definition, T is said to be one-to-one or injective if, now there are two ways it can be stated. So I'm going to state it the first way. So if V1 is not equal to V2, then this implies the T of V1 is not equal to the T of V2. So what this means is if you start with different vectors in the domain, you will end up with different images in the codomain, right? So different vectors get mapped onto different images, right? If the transformation is one-to-one or injective, right? But another way to say it is this: if the transformation is one-to-one, and if the outputs are the same, so if the images are the same, then the pre-images have to be the same, right? So you could define one-to-one or injective in both ways, right? Say if you start with different elements in the domain, then you will end up with different elements in the codomain. You can say, well, if I ended up with the same element in the codomain, then I must have started with the same element in the domain. That's assuming, right? That's the definition of this transformation being one-to-one, right? The second thing that we need to define is the concept of onto. So T is said to be onto or surjective, right? If the range of the transformation is equal to Rm. So if the range of T is in fact equal to Rm, right? So in other words, every element in the codomain is a possible image of some element in the domain, right? And whenever that happens, we say that the transformation is either onto or surjective. Now, based on previous work, we know when this is going to be the case, right? We know actually how to identify if a transformation is onto. It has to do with the number of pivots in our reduced row echelon form of the standard matrix of the transformation, right? If we start with the standard matrix and we reduce it and we have the right number of pivots, right, then we can say whether the range is equal to the entire codomain or just a subset of the codomain. Now we'll actually say that later on in this video. But we already have what we need to identify when a transformation is onto. We don't, as yet, have a nice way of identifying when the transformation is one-to-one. But in fact, that's going to be our first theorem. We're going to prove a theorem that actually shows how easy it is to identify when a transformation is one-to-one, right? So let's start with this theorem. And it says the linear transformation so the linear transformation that goes from Rn to Rm is one-to-one or injective if and only if the kernel of the transformation is simply the zero vector. So if the kernel consists of only the zero vector, then it turns out the linear transformation has to be one-to-one. And if it is one-to-one, then the kernel has to be just consisting of only the zero vector. All right. Now this theorem, it's an if and only if, so it requires us to prove two statements. So we're going to start by assuming that the transformation is one-to-one, and therefore prove that the kernel has to consist of the zero vector. And then similarly, we have to prove another statement that if the kernel consists of just the zero vector, then the transformation has to be one-to-one. So there are actually two things in one that we have to, there are two statements here in one theorem we have to prove both ways, right? So let's start by, suppose T is one-to-one, right? Well, what do we know, right? Now, going back to one of the properties of the linear transformation, so let's say, so suppose T is one-to-one, and let V be an element in the kernel of T. What we would like to show is that V has to be the zero vector, right? If that's the case, then yeah, we've established that part of the theorem. So we know that, and this was one of our properties, we know that when you take the transform of the zero vector, you get another zero vector. This was one of our properties of the linear transformations, right? So we know this. Now, since V is in the kernel, then we know, so actually I should say since, not if. So since V is in the kernel of the transformation, we know that the image of V must be the zero vector, right? So this is saying, so we know that the transformation maps the zero vector onto the zero vector. This was a property that we proved earlier. By definition, any element in the kernel of the transformation must also get mapped onto the zero vector. But we know that the transformation is one-to-one. So since the output is the same, right? So since T of 0 is equal to T of V, right? And T is one-to-one, then the inputs have to be the same. So then V would have to be the zero vector, right? So again, just to kind of summarize This is due to the definition of our kernel. This is a property that we proved several videos ago. And using the definition of one-to-one, then if these two outputs are the same, then because the transformation is one-to-one, then the inputs would have to be the same. So therefore, the kernel only consists of the zero vector, right? So therefore, the kernel of t consists of just the zero vector. So that proves one direction, right? So we've proven that if the transformation is one-to-one, then the kernel has to be equal to simply the zero vector, no other vector, right? Well, what if we go the other way? So now suppose that the kernel of t is the zero vector, only the zero vector. What we would like to do is to show that the transformation is one-to-one, right? Right now, so if t of u is equal to t of v, where u and v are elements in Rn, though in the domain, right? So suppose the output is the same. What we would like to show now is that the inputs would have to be the same, right? So I'm going to subtract t of v from both sides. So I'm going to write it like this, right? And then you might recall that we have a couple properties of the linear transformation that allows us to combine this into one. So in other words, the first thing I'm going to do is this. I'm going to take that scalar and put it inside the parentheses. We can do that, so take this -1 and essentially distribute it through the t, so it ends up like this. That was our property of the scalar multiplication for linear transformation. Now there's a property about vector addition where it doesn't matter if you add after you've done the transform or if you add before, right? So we have this. So then this is t of u plus -v, which I will write as t of u minus t of v, right? So that means u minus v, right, would have to be in the kernel, but the kernel only consists of the zero vector, right? So this implies that u minus v, right, would have to be in the kernel of t, which means, and we just showed that we're assuming that it only consists of the zero vector, so u minus v must be equal to that zero vector, so therefore u has to be equal to v. So if this is true, right? So if the output is the same, what we've shown is that the inputs would have to be the same. Therefore, our transformation is one-to-one. So therefore, t is 1-to-1, right? So that's our QED. So now what this theorem gives us is a nice and easy way to establish if a transformation is one-to-one. We simply look at the kernel, and if the kernel consists of only the zero vector, so if we only get the trivial solution when we're solving that homogeneous system, then it means that the transformation has to be one-to-one, all right? So now let's actually describe kind of a general process that we can use to identify when one of these linear transformations is both one-to-one and onto, right? So let's say this. So suppose our transformation from Rn to Rm has a standard matrix. Let's just call it A, right? And basically we can identify both of these properties by looking at properties of the matrix A, right? Because every linear transformation from Rn to Rm can be represented by a matrix multiplication, right? So the whole idea is we can think about what happens in the reduced row echelon form of this matrix and talk about number of free variables and the number of pivots, and we can identify these two properties. So if the RREF of A has no free variables. In fact, let me just put this as one bullet point. So if the RREF of A has no free variables, then this means that the kernel of the transformation is just the zero vector, right? So this implies that the kernel of T is simply the zero vector. Therefore, T is 1 to 1, right? Because if you have no free variables, then the solution to the homogeneous system is only going to be your trivial solution, which is your zero vector, right? So if you reduce the standard matrix and every row has a pivot, right? Then or I should say every column has a pivot, then there are no free variables, and therefore the transformation has to be 1 to 1. Similarly, I'll say it this way. Now, we can use the concept of nullity and rank as well. So if the nullity of A is equal to 0, right? The number of free variables, same thing. This implies that T is 1 to 1. All right. Now, what about onto? Well, for it to be onto, we'd have to make sure that the number of pivots, which is the rank of the matrix, would have to be equal to M, right? So in other words, if it's onto, then we want to have a basis that consists of exactly M vectors. And for that to happen, we would have to have M pivots in our RREF. So let's state that. So if the rank of A is equal to M, then this implies T is onto, right? So again, it is very remarkable that these two concepts, number of free variables, number of pivots, can help us to answer these two questions pretty much in one swoop, right? The RREF of this standard matrix tells us everything that we need to know. We just have to know what to look for, all right? Now, it turns out when a transformation is both 1 to 1 and onto, we can actually define the inverse transformation, right? So, and that's really helpful. So if T going from Rn to Rm is both 1 to 1 and onto, then T is invertible, right? T is invertible, so it has an inverse transformation. Well, what does the inverse do? Well, the inverse, so let me again do my nebulous sketches of domain and codomain. So it's like this, right? So basically what happens is T is a transformation that takes elements of Rn and converts it into elements of Rm. If the transformation is both one-to-one and onto, then what it allows me to do is to define an inverse transformation now that would take the elements of Rm and map them back onto the elements of Rn. So, and we use this notation for the inverse, right? And it turns out that the only types of transformations that are invertible are the ones where it's defined by a square matrix. So you're mapping R, so basically your N and your M would have to be equal just for this to be possible, and then we would have to check to make sure that our standard matrix is in fact invertible, right? So note, for T to be possibly invertible, the standard matrix of T would have to be a square matrix. So the standard matrix of T must be n by n. That means it would be a mapping from Rn to Rn, right? So in other words, so that is the dimension of the domain must be equal to the dimension of the codomain. All right. So let's just look at an example of this to kind of wrap this up. So, in fact, let's look at a couple examples. So let's start with one. So let's say our transformation goes from R2 to R3, and the standard matrix is 1, 2, negative 1, 3, 4, 1, right? Well, if you think about this, well, first of all, this is not a square matrix, right? So we know it won't be invertible, but let's see what we can say about whether it's onto or one-to-one, right? If it could be either of them. Let's try to put this in a reduced row echelon form. So I'm going to take R1 and add it to R2, and then I'm going to take negative 4 R1 and add it to R3. So I'll have 1, 2, and then I will have 0, 5, and then I will have, let's see, so 0, negative 8, negative 7, right? And then if I do 1/5 of row 2, right? So that gives me 1, 2, 0, 1, and then 0, negative 7. And then finally, if I do 7 times row 2 added to row 3, then I end up with this 0, 0, right? So the rank of this matrix is 2. So the rank of A is 2, and the nullity is 0. So the nullity of A is 0. So what does this mean? Well, because the nullity is 0, this means that this transformation is one-to-one. So therefore, T is one-to-one. Right? The kernel, right? If, for instance, if I were to set this up with the 0, with a column of zeros here to try to find the kernel of this transformation, I would get that only the trivial solution would work, because I would end up with all my pivots here, right? I'd have a row of zeros at the bottom, and then this would be telling me that my second variable is 0, and if my second variable is 0, then my first variable has to be 0. So t is 1 to 1. Right? But my codomain is R3. I only have 2 pivots, right? So I am missing like a third pivot that would give me a basis for R3. So because my rank, so since the rank of A is equal to 2, which is less than 3, then this transformation cannot possibly be onto. So T is not onto. Right? And for that reason, it can't have an inverse. Well, we know that this matrix can't have an inverse because it's not a square matrix, but this tells us specifically why. It's because this transformation going from R2 to R3 is not onto. So therefore, T is not, it's not onto and therefore not invertible. So T is not invertible. All right. All right, let's look at another example here. So let's say this is a transformation that, let's say this goes from R2 to R2. And let's say the standard matrix is -2, 1. And then let's say -2, 1, like that, right? Well, it's not hard to see what's going to happen here, right? So if we reduce this, so if I do -1/2 times row 1, that gives me 1, -1/2, and then -2, 1. And then if I take 2 times row 1 added to row 2, there's my brackets there, we'll have 1, -1/2, and then 0, 0. So now we do have a free variable. There's only one pivot, right? So this tells me that the rank of A is 1 and the nullity of A is 1. Right? Remember, the rank and the nullity, they have to add up to the number of columns in your matrix. So this tells me that this transformation is not 1 to 1 because the nullity is bigger than 0. So since the nullity of A is, in fact, let's just say greater than 0, that means the kernel consists of more than just the 0 vector. This implies that T is not 1 to 1. Right? And then since the rank of the matrix is less than the dimension of the codomain, so I can't get all the possible vectors in R2, right? So since the rank of my matrix is less than the dimension of my codomain, so this tells me that T is not onto, right? So it's neither 1 to 1 nor onto, definitely not invertible. And in fact, we realize this because if we were to take the determinant of this matrix, we would end up with 0. So this matrix does not have an inverse. So therefore T, this transformation, is not invertible. All right, let's do one last example. So let's say we have, again, a transformation that goes from R2 to R2. And let's say A is now, the standard matrix is 2, -1, 1, 1. Now if we go ahead and if we reduce this, so I'm going to swap these two rows. So if I do row 1 swapped with row 2, That produces 1, 1, 2, negative 1. And then if I do negative 2 times row 1 plus row 2, this gives me 1, 1, and then 0, negative 3. And then I can, so, if I do negative 1/3 times row 2, I can see that I have my pivot, right? So 1, 1, 0, 1, right? So this tells me now that the rank of A is equal to 2. The nullity of A, no free variables, is 0, right? So since the nullity of A is equal to 0, this means that T is 1 to 1. And look, the rank of this matrix is equal to 2, the dimension of my codomain. So since the rank of A is equal to 2, which is equal to the dimension of R2, then this means that T is onto. So the range of this transformation is onto. So the range is all of R2. And since T is both 1 to 1 and onto, it means that T is invertible. So therefore T is invertible. Well, if T is invertible, we should be able to write down the standard matrix of the inverse, right? Now, here is the standard matrix of T, but we know how to find the inverse of a 2 by 2 matrix. So I'll just write it. In fact, let me write it down here. So A inverse, so here is A. It's 2, negative 1, 1, 1. A inverse is 1 over the determinant of A, and the determinant of A is 2 minus negative 1 times the adjoint. The adjoint for a 2 by 2 matrix is this. Right, so we end up with 1/3 times 1, 1, negative 1, 2. Distribute the 1/3. What do we end up with? 1/3, 1/3, negative 1, 2. Right? So now we have a full kind of description of this invertible transformation. So again, it starts from R2, goes to R2, and T is defined by this matrix. A equals 2, negative 1, 1, 1. The inverse of T goes the other way, and it's defined by this matrix: 1/3, 1/3, negative 1. Oh, wait, negative 1/3 and 2/3. I forgot my thirds there. So negative 1/3 and 2/3 there, right? So whatever this matrix does, this matrix will undo it, which makes sense, which is why we call it the inverse. Just like how you say you have the inverse of sine, you have the inverse of cosine, you have the inverse of e, you have the inverse of your square root, you have the inverse of the cube function. All those functions are invertible. Now we're learning which of these transformations are invertible, and it turns out we can tell everything simply by looking at the rank and the nullity and focusing on the domain and codomain, seeing when these things can be 1 to 1, seeing when they can be onto, right? So again, not a lot of new in terms of calculations, but a new concept, and we get to apply our old calculations to this new concept of invertible transformations. Hope you found that interesting. See you in the next video.